Okay. So mappings. So the first point is to describe bijection theta from the set Z equals basically the set of integers to its proper subset E, which is described basically as the multiples of 2 of each integer. We're looking at so I pick theta of x equals 2 times x as our function, which is bijective, and I show this, even though I kind of necessarily show it's mapping because it's obvious it is, but more importantly the injective and surjective part. So theta xi equals theta of x2 implies that 2 times x1 equals 2 times x2, which that further implies that x1 equals x2, and that's how you know it's injective. Theta xi equals x theta of x2 implies that x1 equals x2. Theta is surjective, which we also can show a little bit simple as well. For this type at least, y is in y, there is x is in z such that theta x equals y. So y is in its set like before, and x equals y over 2 from its equation 2 times x equals y. So x is in z implies that x equals y over 2 is in z, which implies that x is in this set divided by 2, so it's everything, so negative 4 divided by 2 is negative 2, negative 2 divided by 2 is negative 1, 0 divided by 2 is 0, so on. And so on. You get the point, 2 divided by 2 is 1, and so on. So that means it's in the image works out. Every element of the image is represented. So it is surjective, and injective, so therefore it's bijective. Describe an injection from a set x equals x1, x2 to xn with n elements to the set z of the integers, so the set of integers. So to describe this, we just say theta of x equals x1, x2 to xn goes to z, so that's like what this problem is asking you to show. Theta of xi equals I is in z, so it's just I. So theta of xi equals I is basically what it is. That's the injection. Check if theta of xi, so the check is just show real quick. If theta of xi equals theta of xj, then that means it implies that I equals j, which implies that xi equals xj. And that's all. It's basically saying that every number has an integer representative, goes to one integer. Is theta surjective? Not surjective, because if y equals negative 1 is in z, there is no xi is in x, including x, such that theta xi equals negative 1 because, basically it has to be positive. That's how I and j as these subscripts work, they have to be all positive, so theta xi equals negative 1 would imply that I equals negative 1, which cannot happen because the form of it's theta of xi equals I. And I can only be between 1 and n. It can be greater than or equal to 1, but less than or equal to n. Anyway, so it can be any positive integer, basically. Because of how it's formatted, at least. Because of how it's based on x1, x2, xn. So that's why it's not surjective, but it is injective. Let theta be the mapping from the set R of the real numbers to the set n of the non-negative real numbers given by theta x equals absolute value of x. Is theta injective? Explain. Yeah, but basically, theta x equals absolute value of x is what you really have to understand from that. But no, theta is not injective, and we can show this with a contradiction. Theta 1 and theta of negative 1 both equal the same 1, because absolute value of 1 is 1 and absolute value of negative 1 is 1. That means theta of 1 equals theta of negative 1, but 1 does not equal negative 1. It's that property from before, where how a basic injection, for how an injective function works. Basically, if theta of 1 equals theta, if theta x1 equals theta x2, then x1 has to equal x2. In this case, they're not equal. x1 is not equal to x2, so if it was injective, then theta of x1 would have to not equal theta of x2 in this case, because 1 does not equal negative 1, which would be x1 and x2 here. If that makes any sense. Hope it does. Is theta surjective? Explain. theta, basically, so it's, again, I rewrite it as r to n, how they defined it. Because theta of x equals absolute value of x. For any y is an n, there is x equals y is an r, such that theta of x equals y, because n is included in a set of real numbers, such that x is greater than or equal to 0, basically. Just for a note of how that n is. But yeah, so for any y is an n, there is x equals y is an r, such that theta of x equals y. Which means that, but then of course, yeah, so the proof goes from here, that means that theta of x equals absolute value of x, which is equal to absolute value of y, which is equal to y. So y equals y, and that's due to also y greater than or equal to 0. So it's it's one of those examples of something that's surjective but not injective, which I think is not as common in when you study this in high school algebra. If you study like the one-to-one functions and all that stuff in algebra and pre-calc and stuff, you have these terms injective and surjective. Well, you have at least injective. You see a lot of injective functions. But in another course, I don't think you see as much surjective but not injective. And then 3 is list elements of the complete inverse image, theta -1 of fifth. So theta x equals absolute value of x, so the inverse will be a negative value and a positive value for a specific. So it's 5, so it's -5 and 5. Those are both, the absolute value of -5 gives you 5, and the absolute value of 5 gives you 5. So those are the set, the two numbers. And finally, let g z to z 5, so it's the set of integers to the set of, Sn is the remainder when n is divided by 5. It's this modular type idea. This gmn equal gm times gn for all integers m and n. And to solve this, you basically set it up. It all fits on page. So, gn, you can rewrite this n goes to Sn, saying g of n is equal to Sn with the modular sign on it, equals remainder of r divided by 5. M equals 5q1 plus 5m, and n equals 5q2 plus 5n. That implies that m times n equals 25q1 q2 plus 5q1 Sn plus 5q2 Sn plus Sm times Sn. Here you have Sm and Sn as your remainders. Sm is a remainder and Sn is a remainder for m and n. Division by q and all that. Well, division by 5. And q1, q2 are the quotient from the division of, so m times n, that means that m times n is equal to, from here, 5, you divide out of 5, you get the whole thing, the expression, plus Sm times Sn. Then that means the quotient here but yeah, Sm times Sn is equal to 5q3 plus r, we get from all this. Oh yeah, so the quotient times mn, that should be g, that's why I see g of mn, because yeah, we want to show g of m times n and then g of m times g of m. So g of m times, so using this information, you have what m times n equals. G of m times n will equal r, which is the remainder of Sm times Sn divided by 5, and you get that from this expression here, which means that Sm times Sn equals, because it equals to r, basically the remainder of, so because Sm times Sn equals 5 times q3 plus r, where r is between 0 and 5. It's less than 5, greater than or equal to 0. And gm and modular multiplication gn is equal to Sm, the modular multiplication Sn, which is equal to remainder of Sm times Sn divided by 5, which is equal to r. It's all shown from how it's done. Because we're letting them that equal to remainder of Sm times Sn divided by 5. And it's not as intuitive as the modular arithmetic example would be, which could be done in a class and all that, but I think that's just see how the work is done in it, try to figure.